Write down this. No, you didn't write it. About that we didn't write. Diagram we had written, I think. What is that? Write down. At every point on a current carrying circular loop, the magnetic field is in the form of, write down, and then be quiet now. Is in the form of concentric circles. Concentric circles around it. Okay. As we move away from it, the circles.
She's asking what is log. That's loop.
It's
very log.
LOOP.
Log.
From yesterday, I am shouting loop. How it will become log? You should have some common sense also, no? Right. As we move away from it, the circles would become large and large. Move away from it, the circles would become large and large. And larger. At the center of the loop, the field appears to be in straight line. Appears to be a straight line. Okay. Then the magnetic field. See, as we move, that means the point, for example, there is a circular loop. Okay. Okay. So if you consider a point little bit away from that, what happens? The loop, the magnetic field will be of the larger loop side. So there, the concentric circles will be big. And here it will be like this. At the center, when you come, the loop will be bigger, correct? That I'm trying to explain. If you want, you can write in the other words also. Okay. The magnetic field is directly proportional to current. Directly proportional to the current through it. Current through the conductor. Current through the conductor. Okay, so that is B is proportional to I. Magnetic field is directly proportional to the number of turns. of the wire. Okay, so V is proportional to N. What is the reason? Write a note. This is because sometimes they ask reason and all, then you should write that. This is because the current in each turn is in same direction, and hence magnetic field is also in the same direction. That is, all the magnetic fields are in the same direction. Okay, magnetic field in each turn is in the same direction. Hence, the magnetic field produced in each turn adds up. Last one, right? Magnetic field is inversely proportional to the distance from the conductor. Next, we will study about magnetic field due to a solenoid. Okay, written. So, magnetic field due to a current carrying solenoid. Solenoid, it is having the many number of turns. That is a copper wire. Okay, when a copper wire, it is wound like this, like a spring. How the spring looks like that, no? So solenoid looks very similar to that. How the spring will be wound in the circular turns, right? That many turns will be there. Similar way, the same way the solenoid also will go. Okay, so that has the copper wire, insulated copper wire. Why the insulated copper wire they are telling? Because when you turn the wire here, it will be not shorted. When you wound an insulated copper wire, then at these points it should not short. That is why. So whenever you are considering, okay, so first thing, solenoid is it has many circular loops. It is made up of insulated copper wire.
Okay. Should it always be copper itself?
You can use gold also. It is not economical. No, many times we use copper only.
Or like, can we use iron?
Iron, not for this, I think, because magnetic field, no. When you use iron, which attracts to the magnetic field, then maybe the parameters will change. Yeah, you can use aluminum.
Oh, yeah.
You can use it. Okay, because iron, it is attracted by the magnetic field. No, sometimes the parameters of that may change. So here first we'll use copper wire. Okay, then inside that we can use the iron rod. That will come. I'll tell that. Okay. Reason here now. A copper wire is wound in the form of a spring or a circular turns. It has many circular turns, maybe 50 to 100 circular turns. Okay, and it is made up of insulated copper wire, so that when it turns, no, it will not get short. That is the reason, and that we call it as a solenoid. So when current is passed through that, what is the magnetic field inside that? When through any conductor, if current is passed, magnetic field is produced. So how is the magnetic field in a solenoid? And the magnetic field in a solenoid is very similar to a bar magnet. Okay, the magnetic field lines in a solenoid is very similar to the magnetic field lines of a bar magnet. That means when current is passed through a solenoid, it behaves like a bar magnet. Again, I repeat, solenoid, it is made up of insulated copper wire, and the copper wire is wound many number of turns in the form of a circular turns, maybe 50 to 100 or more than that also. Okay, so it is made up of insulated copper wire, so that when it comes here, it will not short. That is the reason they tell that insulated copper wire. And when current is passed through a solenoid, it behaves like a bar magnet, because the magnetic field lines around a solenoid is very similar to the magnetic field lines of a bar magnet. Bar magnet, okay, has two poles like north and south. Similarly, in a solenoid, the two poles will be formed, that is north pole and the south pole. Okay, and if you observe, the current is flowing in this direction, right? From positive to negative. Current, we always say the conventional direction, that is, it is flowing from the positive terminal of the battery to the negative terminal of the battery. So wherever it is current direction is there, no, that will be the south pole. That will be the south pole. That will be the south pole, and wherever the current is coming in that direction, there will be the north pole. Always you have to write like this. All these they will see. Okay, so in a solenoid, the current in this direction it is flowing, right? So in this direction there will be the south pole, and the current is coming out of this loop. So here it is the north pole, and magnetic field starts from the north pole and terminates at the south pole. And also inside the solenoid, magnetic field will be constant. In the bar magnet also we observed, the inside the bar magnet, the magnetic field was constant, right? So inside the solenoid also, the magnetic field will be constant. That is the same throughout the solenoid. And at the outside the solenoid, at the poles it will be more, at the center it will be less, because it is crowded at the poles. Okay, and now if see here solenoid, if you pass the current through that, it behaves like a bar magnet. If the current is not passed through that, then it is just the copper wire. So here, whenever it is required, we can get the magnetic field. Whenever you can control the properties of anything, that will be used more. See, whenever we can control the properties of any substance, then it can be used more. Okay, so it is used for as an electromagnet. It is used many times as an electromagnet. So what is an electromagnet? When an electric, what do you call, when an iron rod, okay, when a soft iron rod is kept inside an electromagnet, when a soft iron rod is kept inside an electromagnet, inside an solenoid, this behaves like an electromagnet. Electromagnet means when current is passed through that, it acts like a magnet. When no current is there, it is just an iron rod. Okay, so this property is used in many devices. One of the devices is in the bells. Earlier, they used the bell, in the bells. They used the soft iron rods only. They used to use for the bells and all. Okay, the other place is to separate for the segregation of the magnetic materials. See, whenever all the electronic substances will be there, they have to segregate. Correct. For the recycling and all, they have to segregate the particles separately. To separate the magnetic materials like iron, they use this electromagnetism. Okay. So when the bulk is there, when they keep the electromagnet near that, it will attract all the iron substances or maybe the cobalt. Then you move that electromagnet to somewhere and just switch off the current. What happens? All the particles will fall down. So segregation of the magnetic particles will be easy using the electromagnet. Okay, understood now? So how an electromagnet is formed? When soft iron rod is kept inside a solenoid, it behaves like an electromagnet. That means when current is passed through that, it behaves as a magnet. When no current is passed through that, then what happens? It is just an iron rod. So that can be used for the segregation of the magnetic materials. That is, it gets magnetic materials gets attracted to that, and when it is moved to the some other place and just switch off the current, what happens? All the particles will be separated. You can separate that. Okay, so they are also used, and it is used in many other places also. Why we can use those? Because we can alter its properties. Okay, we can alter its properties. Whichever we can alter the properties, adjust the properties, there it can be used widely. Even in the semiconductors, there the conductivity of the material can be changed depending upon our needs. So that is why now widely semiconductors are used. Okay, so where we use the semiconductor in any electronic thing, you will have the semiconductors. Maybe the TV, computers, all most of the electronic devices, we use the IC chips. In that IC chips, we use the semiconductors. Why we are widely able to use that? We are able to control its properties, that is, its conductivity, direction, everything. So whenever you are able to something control its properties, it is used widely. Even the solenoid is the same. Okay. Diagram it is written. Solenoid. Right now. What is there? What she's doing? See, let them do. See, if you listen, it is for you. If you don't listen, you have to sit and study. It will take more time. Okay, you're wasting time here also. You will have to waste time, more time. Anyway, you are already in the shortage of that time. So you will be in the trouble. Don't worry about others. Their headache again, they want to study, let them study. Anyone I'm telling, if you are not listening to the class, again you should go, again you can read it. It's not like you can't read. It will take more time. It depends on you people. If you want easily, you want to do the things are a hard way you want to do, you can do. What is wrong in that? That's no. You should think what you want. Okay. Write down. A magnetic field due to current in a solid. So don't worry about anyone. They listen or not, you people start listening. Like if you people start listening, then it is easier for you only. Okay. And think now, only think about getting more than 1995. Keep that as motto and start doing the things. Okay. A solenoid is defined as a coil consisting of large number of circular turns of insulated copper. Of insulated copper. These turns are wrapped closely to form a cylinder. So the field lines are similar. The field lines are similar to a bar magnet. They are similar to the bar magnet. Okay. The solenoid behaves behaves as if it has it has north pole and south pole. It has north pole and south pole. Then the strength of the magnetic field is same. It is same. That is uniform inside the solid. Inside the solid. Okay. So here also B is proportional to I, B is proportional to N. So if you consider in a one turn magnetic field produced is B, then if number of turns is 100, then 100 into the B. So that is magnetic field adds up in all the turns. Okay. So B is proportional to I, B is proportional to E. And inside the solenoid, magnetic field is always constant. It's same in the bar magnet also. Outside the solenoid, at the pole it is more, at the center it will be less because field lines are more at the pole than at the center. So next, electromagnet. Actually, magnetism and electricity both you have in 12th. You learn more there about these things. Write down this. Right. Write down this.
How can iron not be soft?
It is not the soft means it can bend. That is the soft iron material where the changing the orientation of electrons is easy. Okay, it is not does not mean you can bend that rod. It does not mean that the soft iron rod if you take it making that magnet is easier. That's why we use that soft iron rod. That is one type of the material what we use. Okay. Right down the strong magnetic field produced. The material is not soft. It doesn't mean it is soft. It means it can't bend. It is not that. Okay. It is the type of the iron material where you can change the orientation of the electrons easily. Okay. Electrons orientation. Huh? Is that? What is that? Okay.
You want to
It acts like a magnet. And that time it acts like a magnet. So, it's easy to have that. Okay. It does not mean you can bend the right down. How much you people will be talking? Hmm? When I ask the question, you people will not tell. Huh?
Here we will end the today's class. Do not forget to subscribe the channel. If the content of this channel is useful, please like the video and share with your friends. Thank you.